4 astronauts, a spacecraft circling the moon, and a discovery so profoundly unexpected that mission control fell silent for 11 seconds. Not because of a malfunction, not because of a system error, but because of what they saw on the surface. Something that contradicts every geological model we have built over 50 years of lunar science. Something that forces a question so fundamental, it reaches back to the very origin of our world. The moon is not what we thought it was. For most of human history, the moon was a god, a lantern, a mystery hanging just close enough to touch with the imagination, but far enough to remain forever sacred. Cultures across every continent watched it rise and fall and drew their calendars, their planting seasons, and their entire relationship with time from its rhythms. It was our first clock, our first compass, the original object of human wonder. Then, in the mid-20th century, we stopped worshiping it and started studying it. The results were, for a time, clarifying. Between 1969 and 1972, 12 human beings walked on the lunar surface. They brought back 382 kilograms of rock and soil, the most carefully analyzed geological samples in the history of science. Laboratories around the world spent decades examining those samples, probing them for secrets. From that work, a coherent and authoritative picture of the moon emerged. The moon formed approximately 4.5 billion years ago. A Mars-sized body, which scientists call Theia, collided with the early Earth in a catastrophic impact so violent that it vaporized rock and hurled debris into orbit. Over millions of years, that debris coalesced into the pale sphere we see today. The interior of the moon cooled, volcanic activity subsided, and roughly 3 billion years ago, the moon essentially became geologically dead, a frozen record of the solar system's violent youth, preserved in perfect airless silence. That was the story. Solid, evidence-based, peer-reviewed 1,000 times over. What could change it? The Artemis program was not designed to challenge that story. It was designed to build on it. When NASA and its international partners began planning the return of humans to the moon, the scientific mandate was ambitious but focused. Investigate water ice at the lunar South Pole, study the radiation environment for long-duration habitation, and characterize the regolith for in-situ resource utilization. Practical goals. Forward-looking goals. The science of a species preparing to stay, not simply visit. Artemis I launched in November 2022, an uncrewed test flight of the Space Launch System and the Orion capsule. It circled the moon in a distant retrograde orbit and returned to Earth, and the vehicle performed beyond expectations. That success cleared the path for Artemis II, the first crewed lunar flyby since Apollo 17 in December 1972. 4 astronauts were selected for the mission. Commander Reed Wiseman, a veteran of the International Space Station with over 200 days in orbit, pilot Victor Glover, whose background in naval aviation and spaceflight operations made him one of the most prepared humans ever to approach another world, mission specialist Christina Koch, who holds the record for the longest single spaceflight by a woman, and Jeremy Hansen of the Canadian Space Agency, the first non-American to fly on a deep space mission. Their trajectory was designed to bring Orion closer to the lunar surface than Artemis II had traveled, not to land. That mission falls to Artemis III, but to survey, to observe, and to prepare the ground, both literally and scientifically, for the missions that would follow. The approach to the moon on the mission's 6th day was scheduled as a largely nominal event. The crew would observe, photograph, and record. The science teams on Earth would correlate visual observations with orbital data from the Lunar Reconnaissance Orbiter, which has been mapping the moon's surface in extraordinary detail since 2009. It was, in mission planning language, a characterization pass. What happened during that pass was not characterized in any mission document. To understand what the crew encountered, we need to understand what they were looking at. The lunar South Polar region is among the most scientifically compelling locations in the inner solar system. Permanently shadowed craters, regions that have not seen direct sunlight in potentially billions of years, hold water ice in quantities significant enough to support human presence. The terrain is ancient, tortured, and beautiful in the way only truly alien landscapes can be. Craters overlap craters. Ridgelines rise sharply against the absolute black of space. The light, when it exists, comes in at permanent low angles, throwing everything into long, dramatic shadows. Scientists call this region the South Pole Aitken Basin's periphery, and it is one of the oldest surfaces on the moon, perhaps the oldest accessible surface anywhere in the inner solar system. The rocks there preserve a record going back to within a few hundred million years of the moon's formation itself. That antiquity was supposed to mean stability, predictability, a place where we would find exactly what we expected. Ancient impact melt, frozen volatiles, undisturbed regolith measuring out exactly the story we already knew. Instead, the Artemis II crew found something that had no business being there at all. Before we can understand the magnitude of what was found, we need to understand what impossible means in the context of lunar science. Because science is a careful discipline, and scientists are careful people. They do not use that word lightly. When a scientist says something is unexpected, they mean it falls outside the probability distribution of current models. When a scientist says something is anomalous, they mean it requires explanation. But when 4 trained astronaut scientists orbiting the moon fall silent for 11 seconds before reporting to mission control, something fundamentally different has occurred. Something has broken the model entirely. The data chain that led to the discovery began not with human eyes, but with an instrument, Orion's optical navigation system, designed primarily to assist with trajectory calculations, uses high-resolution cameras to image the lunar surface during close approach. On that approach pass, those cameras captured a surface feature that did not match any cataloged formation in the Lunar Reconnaissance Orbiter database. Understand what that means. The Lunar Reconnaissance Orbiter has been circling the moon since June 2009. In that time, it has imaged the entire lunar surface at resolutions as fine as 50 centimeters per pixel. It has produced the most comprehensive map of another world in history. The South Polar region, especially, has been imaged repeatedly at multiple angles under varying illumination conditions. Every crater, every ridge, every boulder field of significant size has been cataloged. The feature that Artemis II captured was not in the catalog, and it occupied an area approximately 4.3 kilometers across, large enough that its absence could not be explained by resolution limits. Something had changed on the surface of the moon, or something had been overlooked in a way that defies the capabilities of one of humanity's most sophisticated orbital observatories. The mission science team on Earth scrambled to cross-reference. They pulled thermal imagery from the Diviner Lunar Radiometer experiment. They queried radar data. They examined elevation maps with centimeter-level precision. What they found was both reassuring and deeply disturbing. Reassuring because the feature existed in older data, disturbing because it had changed. On the moon, nothing is supposed to change. Not on human timescales, not without an external cause. No impact had been recorded, no event large enough to explain the transformation. And yet the data showed something undeniable. The thermal signature had shifted. In earlier observations, the region behaved exactly as expected, brutally cold in shadow, scorchingly hot in direct sunlight, cycling with mechanical predictability as the moon rotated. But in recent passes, the region was warmer, not dramatically, but measurably, consistently, in a pattern that could not be explained by instrument error. Something beneath the surface was generating heat on a world declared geologically dead billions of years ago. How do you process that? You check the instruments. You check again. You request independent verification. You assume error. But the anomaly remained, and then came the closest pass. When Orion descended to its nearest approach, the crew saw what the data had not fully prepared them for. The region was not uniform. It had structure, not the chaotic randomness of impact craters, not the frozen flows of ancient volcanism, but geometry, angular regularity, consistent orientation, features that did not match any known natural formation process on the moon. And that is when everything changed. Because geology produces patterns, but not precision. It produces shapes, but not order. And when something cannot be explained within known processes, the model itself becomes the question. That is the moment when science stops being confident and starts being curious again. And what made that moment even more unsettling was not just the geometry itself, but the context surrounding it. Because if this were an isolated feature, something that appeared randomly, something that could be dismissed as a rare geological formation, the model might still hold. But it was not isolated. There was heat, there was structure, and now there was pattern. That is when the investigation moved deeper, beyond the surface, into the interior of the moon itself. Because decades before Artemis II ever approached the lunar South Pole, the moon had already been sending signals. Signals that were recorded, archived, analyzed, and then quietly set aside because they did not seem urgent at the time. During the Apollo missions, astronauts deployed seismometers across the lunar surface. These instruments recorded thousands of moonquakes, small tremors that rippled through the moon's interior. At first, everything about these signals seemed explainable. Some were caused by thermal expansion as the surface heated and cooled. Others were the result of tidal forces exerted by Earth's gravity. But when scientists mapped the locations of these moonquakes over time, something unusual began to emerge. They were not random, they formed patterns. More specifically, they aligned, a curved, continuous structure deep beneath the lunar surface, stretching across regions that, at the time, did not seem connected in any meaningful way. And when that structure was projected upward, aligned with surface coordinates, it passed directly beneath the region that Artemis II had just observed. That is not coincidence, that is connection. That is the point where independent data begins to converge into something larger. Because now you do not just have a surface anomaly, you have a subsurface structure, you have a pathway, and pathways imply movement. At this point, the model begins to strain under its own assumptions, because the moon is supposed to be static, stable, inactive. And yet, here is evidence of alignment, of continuity, of something that extends beneath the surface and connects across distance. But even then, it might still be explainable. Stress fractures, residual structural weaknesses, remnants of ancient geological activity frozen in place. That explanation feels safe. It preserves the model until the final piece appears. Water vapor, detected not as a trace, not as a background fluctuation, but as a measurable increase in concentration directly above the anomalous region. That should not happen. The lunar surface does not support sustained vapor. Temperatures are too extreme. The atmosphere is too thin. Any exposed ice sublimates slowly over time, but not in concentrated bursts and not in patterns tied to a specific location. Which means the vapor was not coming from the surface, it was coming from below. Now the system becomes unavoidable. Heat beneath the surface, a structural pathway extending through the interior, and water moving upward through that pathway. Individually, each of these could be explained. Together, they form something else, a process, a system, something still active. And that is the moment when the original assumption fails completely. Because a dead world does not have systems, it does not move, it does not circulate energy, it does not change, but this does. And that forces a deeper question, not just about the moon, but about everything we thought we understood. Because if the moon still contains internal energy, then our understanding of planetary cooling is incomplete. We believe that smaller bodies lose heat quickly, that they become inactive, that they transition into stability. But if the moon has retained enough energy to drive localized activity, then that assumption is not universal. And if it is not universal, then it cannot be applied to other worlds with confidence. Mars, Mercury, rocky planets orbiting distant stars. Worlds we have labeled as inactive may not be inactive at all. They may simply be quiet. And quiet is not the same as dead. Quiet means hidden. It means that whatever is happening is not visible at the surface. And that is the realization that changes everything. Because it suggests that we have been looking in the wrong place. We have been studying surfaces, reading them as complete records, assuming that what we see is all there is. But the moon is showing us something else. It is showing us that the surface can lie, not intentionally, but structurally. It can hide what is happening below. And if that is true, then the number of worlds that may still be active, still evolving, still chemically dynamic, increases dramatically. That changes the search for life, because life does not require sunlight. It requires energy, it requires gradients, it requires environments where chemistry can become complex. On Earth, those environments exist deep beneath the surface, in hydrothermal systems where heat, water, and minerals interact. If something similar exists beneath the moon, even in a limited form, then the boundary between active and inactive worlds is not as clear as we thought. This is not proof of life, but it is proof of possibility. And possibility is enough to shift the direction of science. Because once a possibility exists, it must be tested, it must be explored. And that is what happens next. Future missions will target this region with a different objective, not just observation, but investigation. Artemis III will land near the anomaly. Astronauts will collect samples directly from the surface. They will drill, they will measure temperature gradients. They will attempt to trace the pathway from the surface into the interior. Other missions will deploy ground-penetrating radar. They will map structures beneath the surface. They will search for continuity, for patterns, for confirmation that what we are seeing is not an isolated event, but part of a larger system. This is no longer exploration. It is a controlled attempt to answer a question that should not exist. What is happening beneath the moon's surface? And yet, even with all of that, one problem remains unresolved: the geometry. Because heat can be explained, water can be explained, seismic alignment can be explained. But precise repeating geometry is harder. It suggests order, and order implies a mechanism, something that produces consistency, something that shapes material in a predictable way. And right now, that mechanism is unknown. It may be natural, it may be rare, it may be something we have not yet observed in other environments, or it may represent a gap in our understanding so fundamental that it forces us to rethink how planetary surfaces evolve entirely. And that is where the story stops being comfortable. Because science depends on models, and models depend on consistency. But when data begins to fall outside those models, the response is not immediate rejection, it is revision. Slow, careful, methodical revision. And that is what is happening now. The moon is no longer a solved problem. It is a question again, a question that reaches deeper than expected. Because it is not just about what is happening on the moon, it is about how we understand worlds in general. And that is why Mission Control went silent, because in that moment, they were not just looking at an anomaly, they were looking at the edge of their own understanding. And sometimes the most important discovery is not the thing you find. It is the realization that what you thought you knew was incomplete, that the model was not wrong, but it was not finished, and that somewhere beneath the surface of the moon, something is still moving, still changing, still waiting to be understood. And until we understand it, the moon is no longer a memory of the past. It is part of the present, and possibly part of the future.